Hello, everyone, and welcome to our first vLLM office hours of 2026. Hard to get used to saying 2026. It is the first week. I know that it's been probably a busy holiday season. Red Hat had a very nice recharge time. We typically don't work between New Year's, so we were completely off. I was just telling Michael I came back to only 50 emails, and I get pretty much that a day, and no Slack messages. So we totally took some vacation time, and we're really excited to be back with you this month. We're joined by Wentao, who is a vLLM committer from Red Hat, and Bram Wasti from Meta. Welcome, Bram and Wentao. Bram will speak about the batch invariance in vLLM, and then you'll see that in a few minutes. And then Michael, welcome, man. Good to see you. I know you've been snowboarding. You're the familiar face here. Good to see you, of course. So if actually I can just go to the next slide. So we do have a quite packed schedule for vLLM office hours in January. Typically, if you're new to the office hours, oh, by the way, if you're new, I'm Sasha. I've been kind of a host for these office hours. I work for Red Hat. I love vLLM, of course. But anyway, so we'll have a quite busy schedule for vLLM office hours in January. Typically, we do these every 2 weeks, but because of some scheduling issues and just overwhelming interesting topics, we'll have a session every single week in January. And hopefully we'll go back and give you a little break and go back to our regular bi-weekly schedule in February, although no promises. There's still a big list of topics. So anyways, I just want to say that on December 18th, 3 weeks ago, we had a great session on vLLM 2025 retrospective and 2020 maps. Simon Moe from UC Berkeley and Michael and myself talked about this. I did link the slides and the video there. The slide is in the YouTube description. You can always find the slides in the YouTube description, by the way. So definitely check it out. Happened in vLLM 2025, from model usage, hardware usage, key things accomplished, and then what we're thinking about 2026, definitely worth a look. And then today we're talking about the batch invariance, as I mentioned, and then the following week, January 15th, we'll talk about Speculators, a library that's been out for a few months now that lets you build and store speculative coding algorithms. On the 22nd, so 2 weeks from now, we'll talk about LLM compressor. Again, these are typically quite popular sessions. We'll give you a LLM compressor update. The project is really seeing a big uptick in usage, GitHub stars, installs. So there's a lot of good new stuff, and the team is very excited to talk to you about that. And then lastly, and this was something that was just released, and maybe, I'm not sure, I think, Michael, you might cover it. I haven't seen it, but maybe you will, is the vLLM CPU offloading connector. I saw that promoted and blogged about on X. We'll have the actual person who made that commit to come and speak to us about it on January 29th. Anyways, Michael, I'm going to pass it to you. What's going on?
Yeah, it's a busy start to the year. Thanks for the introduction, Sasha, and good to be back. Yeah, we have a lot to cover. We had a release just before the end of the year, and a new one on the way. So we'll cover that next time. But also releases from the other projects inside of vLLM. So we'll cover those before we get to the special topic. But let me go ahead and get started. So if you aren't familiar with vLLM, it's the industry standard for open source LLM model serving. The most popular open source LLM engine for production deployments. Over 60,000 GitHub stars, an insane amount of PRs every month. Millions of GPU hours deployed every week. Yeah, now 2,000 contributors, which I'll briefly cover, and tons of members in our Slack and developer forums and whatnot. And yeah, it gets exactly its power because it's a Apache 2.0 project. Contributors from many different companies. We're part of the PyTorch Foundation and work really closely with Meta and PyTorch folks. To build that ecosystem very closely within the PyTorch ecosystem. And of course, as a LLM inferencing library itself, it's popular because it's easy to use. It's a pip install away, a Docker run away. Supports hundreds of different model architectures, all the open source state-of-the-art model architectures, deploying those across not just NVIDIA GPUs, but a variety of hardware accelerators with the hardware plugin backend, deploying those models across not just one device, but multiple devices with different types of parallelism, like tensor parallelism or context parallelism, or disaggregation of prefill and decode. Yes, vLLM was originally developed in Berkeley Skylab, to answer the question. And of course, vLLM itself is one project inside of the overall project ecosystem of LLMD, vLLM-Omni, GuideLLM, Speculators, and many more, which we'll cover a bit of those thanks to their recent releases over the past 2 weeks. And the first one I want to cover is one of our newest projects in vLLM, which is vLLM-Omni, which is tackling building pipelines around vLLM still as sort of the autoregressive LLM backbone core, but now dealing with these omni-modality models or modality output models that are having diffusion transformers or diffusion models or VAEs, or other things on the encoding or decoding parts of the model. And it still hasn't had a proper official release yet, but the 0.12.0 RC1 is the first official pre-release that we actually feel good about. And there's been a lot of progress in that new repo. So if you want to get involved in the vLLM ecosystem, it's a really great place to pick up and get a lot of ownership and a new part of the project. Really, there's been a lot of usability and enhancement to supporting more of the OpenAI style APIs, like if you've used the DALL-E models before or the image generation from OpenAI, sort of supporting those as an application level. And adding the AMD ROCm support was a really big focus for this release and building up to an official release hopefully soon. Next, the vLLM semantic router project is another pretty popular project. Ultimately focused around building pipelines and routers and guards around models that you're deploying, so that you can deploy multiple models from small to large, and as you have requests coming in, hopefully dispatch and route to the models that need to deal with harder requests to answer or simpler requests to answer, much like GPT, ChatGPT 5, where it automatically routes to small flash models or sort of more heavy, longer thinking and longer latency thinking models. This has seen a lot of interest in large scale deployment and enterprises, and is also a very active and community oriented project, and has had its first proper official release with a lot of fanfare about it. So recommend starting to take a look at it now, and it's just a pip install away as well. So hopefully you can try it out and maybe build a fun demo with it. Another thing I want to call out is we've been noticing and have been very thankful for the many re-implementations of vLLM that have been coming up in the open source community. We think this is like a really good project for anyone to do, just to build their own skills, but also a really great thing for people who just want to understand more about the fundamental operations and structures that make vLLM what it is, with much less lines of code. I think like nano vLLM is like under like 1,000 lines of Python, and still gets like really good performance in a lot of similar cases compared to vLLM. So while there's reasons why vLLM is the size and complexity that it is, a lot of the core ideas are actually rather simple, at least in code, and reading some of these simpler implementations will definitely help you, and it helps us just better understand what are the core ideas and DNA of vLLM, and the abstractions that ultimately we want to make sure are well codified and understood by both developers and also deployers of systems like vLLM at scale, to hopefully understand a bit more about the black box and the right assumptions to make about the behavior of the system and the scheduler, the engine core. So yeah, lots of love to these great projects. Now I'm going to cover what's new in the last vLLM release since the last office hours. Thankfully, we have a pretty regular bi-weekly schedule now, so this one isn't too big, but it's still pretty big, over 440 commits, over 200 contributors, and 61 of those brand new contributors into the code base. We have a decent bit of new model support, particularly the Bagel model is pretty interesting from the autoaggressive side. That's going to be hopefully added to vLLM-Omni on the diffusion side. And also, there's been some updates to the Nematron models for their new MOE architectures. And also to note, we've officially landed the official embedded DeepSeek v3.2 tool parser, which is quite complex, and introduces some new tags inside of even the OpenAI API, or like the chat completions API rather than just the user. So really important, if you're interested in deploying that model, definitely check out the specific tool parsers we have there. And we've been making a lot of progress on speculative decoding, adding more types of Eagle and other draft or MLP speculator-based models, and even expanding them to the transformers general model backend, as we're trying to support these speculative models without needing to hard code for every single model architecture that we're supporting. And the transformers backend is hopefully a more general way that we can get through and do that. Another really big feature that we've landed is this compilation via compile ranges. This is allowing us for when we use torch compile with vLLM. Generally, we compile one dynamic shaped graph, and we do all of our operations within that dynamic shaped graph. However, there's some cases where we want to do kernel fusion. We want to make different choices of kernels to dispatch to and what kernels to fuse and not to fuse within different ranges of batch sizes. So the compilation ranges allows us to compile like 2 or 3 torch compile graphs at different batch sizes, and allows us to do optimal fusions for low latency cases and do different fusions for high throughput cases. We call this sort of an inductor partitioning, and this isn't enabled by default yet, but we are certainly working to do that hand in hand with the torch compile team. We need to reduce the compilation time a bit to make it better on by default, but you can enable this manually yourself. Another thing to note is we have been working on expanding the amount of attention types we can support, and most notably the prefix LM support for flex attention and Triton attention is pretty critical, as some pretty important multimodal models have started coming out using prefix LM, which is quite different from just normal causal attention. And while these aren't our most performant attention backends, still getting the right correctness for these models is an important first step, and hopefully it'll drive repeated improvements and performance within those attention backends for people that start running into bottlenecks with those models. Next, we've been making pretty good progress on the Model Runner v2 backend, filling out the sort of sampling support there. It's in a relatively good state for simple model execution on a single node without speculative decoding. And now, we sort of build towards filling out the advanced CUDA graph support and speculative decoding support in there. So expected to take a few more months, hopefully, at worst, but we are making good progress there, and it is usable in some cases. As I mentioned, we've been optimizing speculative decoding. We've also been optimizing Whisper models quite a bit. We've seen a really large performance uplift since the past release, and I've even added CPU backend support. And I think last time I checked the model metrics, Whisper is number ninth, like most deployed model on vLLM right now. So it's definitely a lot of people are getting a lot of usage on it, and powering some of our transcription services at scale. Yeah, that's all for this slide. We've been pushing, consistently a lot of hardware and performance optimizations, especially on NVIDIA Blackwell and DeepSeek models. There's been a lot of performance uplift thanks actually to Wentao here on the DeepGem kernel performance. So a lot of those improvements, through the sort of model bash work stream. We've been pushing, DeepSeek performance and some other model performance, particularly on Hopper and now focusing on Blackwell. So expect to see continued improvements there for DeepSeek and other MOE models. And particularly, we're building up for Blackwell Ultra support. So we now are building, we'll build official images and wheels ready for GB300 next release. But you can already build from source now, and that's well supported within the Docker file. And we're working on tuning the kernels now with NVIDIA there. Yeah, also, on the CPU side, expanding support there, model support, also some performance optimizations. On the AMD side, there's been a good amount of performance optimizations from new quantization kernels, more fusions with Torch Compile, and also a big rehaul of the AMD CI. We're hopeful by the next release, we'll be able to enable a full suite of AMD CI on main. And you'll see a lot more stability with AMD, and hopefully we'll also be able to publish more regular wheels and images for AMD ROCm. And then of course we're still focusing on large-scale serving and disag PD. We've landed support for the Mooncake transfer engine as a new backend for KB transfer. Still improving the resiliency of Nixel for KB transfer, and communication between the P and D nodes, and overall just still tuning the performance and squashing bugs as we scale vLLM to larger disaggregated serving setups. Finally, on the API and front-end side, still a lot of improvements here on the responses API, chat templates, tool calling, trying still to improve the functionality and reliability there, and also provide better support for MCP integrations for the applications building on top of vLLM. We've also been pushing some fixes for the Anthropic API, and I actually recently landed myself a doc on how you can use vLLM to run Claude Code locally with models like GPT-OSS. And a good number of people are starting to use the Anthropic API and vLLM because of that. So yeah, we're really invested in trying to improve the quality of that API for users that are based on using Anthropic models more and more. And we've also had an overhaul to profiling, adding more fine-grained layer-wise NVTX marks, and also overhauling the profiling sort of configuration. Previously, it was all environment variables that you set, and now we actually have a proper profiling config, a variable that you can pass in, and get much more control over the profiling without looking at vague environment variables. And then also to note, we do have a number of breaking changes and deprecations. So definitely before you update your release, make sure to keep up with these. If you're shocked about them, please reference our deprecation policy. These all have gone through that and gone through a few releases of deprecation, and now we are just removing them based on schedule. Most of these shouldn't be that much of a problem. And probably the one I'll mention the most is that if you've been using the vLLM attention backend environment variable, we've added the attention backend, well, rather attention config, and also a specific attention backend CLI arg, and highly recommend using this instead of the environment variable, as yeah, it'll just work much better with the Oracle and heuristics we have for choosing the attention backend. So that's all we have for the last vLLM release. As I mentioned, it wasn't too big, and you know, the big surprise at the end of this is we reached over 2,000 contributors as a result of this release. So really big milestone for the project, and we're really happy that so many people could be a part of vLLM itself. And if you look beyond the project itself, at the other ecosystem projects, it's much more than that. But it's great for a project that's only, you know, 2.5 to 3 years old to have so many different contributors. And we have a little gift. If you have ever wondered about what release your PR has you know, gotten into vLLM, you can now look this up directly by going to vLLM.ai/PR lookup and put in your PR, and it'll let you know what release it was first in. So you can stake your claim that your work has been in vLLM since this time. So yeah, thanks a lot. That's all from my side, and I'll pass it over to Wentao and Bram. Wentao, you want to take it ahead?
Could you see this screen?
Yep.
Yeah.
Okay. Thanks, Michael, for the introduction. Hi, everyone. My name is Wentao. I'm a machine learning engineer in Red Hat. I'm one of the VMS committer as well. And today we are going to introduce you with the batch invariance inside VM. And Bram will take over after that for the reinforcement learning as a real usage. So let's get started with a simple question. Find the greatest real number that is less than something. Even if we set the temperature equals to 0 with the fixed seed, as long as the batch size change, we can get the different answer with the same prompt. And what's worse is that the second answer is the wrong answer. Why does this happen? There are several reasons accounting for this. The first reason is that the rounding errors of the floating points. As we all know that in computer science world, the floating points are represented in a spatial design like this. And this introduces the rounding error. If you're using the low precision like FP16 or BF16, this rounding error becomes larger. And because of this rounding error, we have this non-associativity for floating points. For example, A plus B plus C, we will get a different answer with A plus C plus B. This causes a lot of problems, actually. And because of reason 1 and 2, we can draw a conclusion that the reduction order matters. And for example, here we have 6 elements in an array. If we want to do a sum among these 6 elements, we use atomic aid on GPU scenery. The atomic aid can guarantee that we count for all of the elements, but the order might change each time we call for this function. However, what's luck is that we do not have atomic aid operator during large language model inference forward, which is good for a single request. We can get a deterministic result over one single request. But this is not true when we try to combine multiple requests together. Non-deterministic introduced with multiple requests together. This is from the continuous batching that is commonly used in large language model inference. So let's take a look at the naive batching first. As you can see here, after we have to wait until all of the sentences get done, and then start the next sentence. So if we have the S5, where would S5 be? Yes, the S5 will start with at T9 instead of doing earlier, which is kind of like a waste of computing resources. So we have this continuous batching strategy. Instead of waiting until T9, as you can see here, we can start S5 right now after the first sentences end. If we consider this is a tensor, and originally the S5 would be here, and now it's become to here, this changes the reduction order and then breaks the determinism. Is there any way to solve this? Exactly, the batch invariance. This is a beta feature we just introduced in vLLM recently. As long as we open this environment variable, vLLM batch invariant equals to 1, we can not only have all of the output tokens the same, but also we could even have the log prop difference equal to 0. This batch invariant ensures the output of model is deterministic and independent of the batch size or the order of the requests in a batch. In other words, we have the fixed reduction order, no matter what is the request under a certain position. Let's talk a little bit about how to achieve batch invariance. So the basic idea is to make sure every kernel involving reductions batch invariant. For large language model inference, there are 3 kernels involving reduction dominate. The first one is IM-SNARL, the second one is matrix-MAL, and the third one is attention. We will go through one after another. Let's firstly take a look at the IM-SNARL. There's the reduction here as a mean. We will sum over all of the elements and then do a divide by the number of the elements. In the naive solution, we will do the reduction here. And we will parallel through rows. For example, in a GPU scenario, we will assign 4 threads for this data. And because of the reduction order is fixed, we're starting from here to here. The order is fixed, so it doesn't hurt the batch environment. In large batch size, this works well as well, because we can assign a lot of threads working together, making good use of the GPU resources. However, in small batch size, if we have, for example, 8 threads, and there's only 1 thread working on these features, and there are 7 threads idle, which is a great waste of computing resources. So how do we solve this problem? Some smart engineers have been having this optimization technique called split K. Let's draw a line here. So for example, if we K equals to 2, we will use 1 thread go through these 3 blocks, and then 1 thread go through these 3 blocks, and so on and so forth. Based on this split K technology, we make better use of the GPU resources since we have more parallelism. However, as X grows, the reduction order got changed. Let's for example, if this is not a block of 6, if it's a block of 8, we are still using the original K equals to 2. And now the first thread will go through the first 4 blocks, and the second thread go through the second 4 blocks. And as you can see, previously we used these 3 reduction, and now we use these 4 blocks as a reduction. So the reduction order changes. As we mentioned in the first beginning, this reduction order change can involve the strategy, the batch and not invariant. The easiest way is just not to do the split and keep the original order. So we just do the reduction over this X. And let's talk a little bit about the matrix-MAL. The idea of matrix-MAL is relatively easy. We will iterate through this line and iterate through this column and do a MAL or over of them and do a sum after we get the MAL results down. The naive matrix-MAL follow the batch invariant logic, which is good for large batch as well. For example, if we have 16 threads, and we can assign each of thread to each of the output location tile. But similarly, problem raises when the batch size is small. So if we have 16 threads here, there are only 4 threads working for this small batch size. So how do we solve this? Smart like you must have the similar idea. Yes, we can do the split K optimization. Yes, exactly. In small batch size, we usually optimize using split K. So what does this do is that, for example, we take this small part and do the matrix-MAL and get this partial sum. And we combine multiple partial sum together and get a final result. This can make better usage of the GPU resources. But this breaks the order of reduction as well as k grows. For example, here we have split k equals to 8. If k grows up, and now the grade 1 will cover the whole block instead of half of the block. And this breaks the order of reduction. How to solve this? The easiest way is to compile one kernel configuration and use that for all shapes within the fixed tile and all the fixed split k, etc. Just similar as we introduced for the IMS node before. Let's thirdly talk a little bit about attention. I think most of us must be very this equation. How does this attention work? So we'll basically use Q to matrix map with this K and get these scores, and then use the scores going through the softmax, and then do the matrix map with V, get this output. In Flash Attention 2's implementation, we will do a parallel along Q as a naive solution, which is good because we have the fixed certain order here. Another context we need to introduce for attention is that we have the KV cache. So here we will do a using this Q to do the matrix map with this K, and then combine these all together to make a whole KV cache. So when a new quest comes, it will calculate for K and then combine to the current K cache. Taking a look at this shape, if it's L1D and L2D, the final KV cache will be L1 plus L2D. Similar situation raises when the batch size is relatively small. There are a lot of threads keeping idle for this case. Yeah, so the split K works again. How does that work? For example, if L equals to 1000, and the split, we try to split into 4 parts, and then each part of this would be 250. And then we will do a single matrix map here and get the partial softmax result, and doing this for V as well. This could make us make better usage of the GPU resources. However, the determinism broken as L increases. So as we know that the L will increase when we're having more new requests, and we can draw a rectangle here. If we say, for example, if now L equals to 2000 and the split K is still 4, and each of the block would be 500 instead of 250. And because of this, the reduction inside this 250, inside this 500 is totally different, and thus breaks the determinism. So what should we do? The idea is that we should use a fixed split size to take over this situation. So for example, 256. We will draw a line here as a 256 to make a block, and then block here and block here. And no matter how long it's left, we just make it a single block. After doing this, even if the L increases, we will still have the same fixed split size. So 256 here. We can make a detailed comparison in this picture. In the previous version, we split into 4 parts. And in this version, all of the blocks are still 256. And within this 256 block, is here or is calculated in here, they are all the same, have the same reduction order, which save the batching environment. Great. Let's have a batching environment summary. So basically, the idea is to make every kernel batching environment. In other words, with a fixed reduction order. Not that the presentation is simplified due to time constraints. We haven't covered the topics, for example, like with TP or DP, or with chunk preview or touch compile. Checking with the latest updates, this is a new feature just introduced inside vLLM, and we're growing currently. Any features, optimizations, or model validations, any help is greatly appreciated. And it's relatively simple to get started with contribution to batching environments in vLLM. So for example, we have a model list here. And what we need to do is test the model using the current script we have, and then submit a PR updating this document. We will have more detailed instruction inside this issue. This is the inference for this presentation. That's all about my part. Thank you very much for listening. Let's transfer to Bram for the reinforcement learning introduction.
Cool. Before I take over, it looks like we got some questions that Wentao and maybe I can help answer.
I think we can go on, and I can apply one of each other later.
Okay. Michael, would you mind sharing the?
Yeah, sure.
Thanks.
Hey, Ray, do you have your Ray hand? Oh, there it goes.
I can ask the question?
Yep.
Sure.
So basically, my first question was that, so from my understanding, this is all floating point inaccuracies. So like, what is the real, what is like the demand? Like, what kind of people or industries have been asking you to like be so precise in these floating point inaccuracies? Because from my understanding, it's extremely small, and people shouldn't even rely on these small, one in I don't know, yeah.
Thanks, Ray. This is a very good question, and we will kind of like cover this topic after Bram's topic for reinforcement.
Oh, I see.
Yeah.
I see. I know.
Okay.
Cool.
Please go on, Bram, and we will answer the questions after all of the presentation.
Cool. Yeah, so I guess maybe to quickly kind of address it, separate from what I'm about to talk about, debuggability is obviously a huge deal when it comes to like trusting inference frameworks, which are now very tightly coupled with the training loops of modern LLMs. There's a huge level of accountability that's kind of never been seen before. You can't just run evals and say, oh, it works. You have to show that like, oh, everything's kind of working exactly right, because now people are spending many, many millions, if not billions of dollars to run inference. So I think there's some level of like debuggability and accountability that comes from just having bitwise exactness. But going into a more theoretical reason as to why we might want this, I'm going to talk a bit about on-policy reinforcement learning and some experiments we did by pairing vLLM's batch invariance with TorchTitan, which is an open source training framework maintained by the PyTorch team. Cool. All right, so just to quickly go over some of the basics in reinforcement learning. The basic idea for applying reinforcement learning to LLMs is that you do it at the very end of pre-training and then fine-tuning a model. So in this kind of like way of fully training an LLM, it's almost always the last step. And what it does is it allows the LLM to kind of pick up abilities or refine on its own abilities to potentially reason or use tools, or in other ways kind of get signal and become better at what would typically be a very sparse signal problem. To be more concrete about this, just looking at the slide, we can see that the agent does an action. In this case, the action would probably be something like generating a token, and then the environment gives some feedback. It updates the state, which in this case would be like the context window, and then gives some reward, which I'll talk about later. One thing to note is that you should just kind of ignore these variable letters. They're not used like this in LLMs. But yeah, this is kind of how you might want to think about it, which is that it's this kind of training loop that happens at the very end of training, where the rewards are typically extremely sparse. So it'll just be like good, bad, or maybe just like kind of good, kind of bad. And this model, which often has billions, if not trillions of parameters, needs to derive information from that and get better. So that might give some insight into why you really want to be very precise with this stuff. But going forward into what LLMs actually use for the reinforcement learning, kind of this is basically ancient history at this point, but PBO was kind of the first derived way of applying reinforcement learning to the very last training step of an LLM. And what it does is it takes this policy. So you can imagine the LLM itself would be represented by this pi parameterized by theta, which then has some action dependent on some state, which would basically be generate a token based on your context. And then you pair that with an advantage function. And so advantage is effectively the same thing as reward. You can think of it that way. And these functions were, in the PPO case, defined by often learned value functions. So it's kind of tricky to do that because you have to learn a model that's able to judge what an LLM is doing. And as far as we can tell, LLMs are pretty much the smartest thing we're able to train machines to do. So it became very tricky. Oftentimes what people would do is they'd like somewhat overfit an LLM that could do value analysis. Typically, or more often, they would just have data sets that had kind of ground truth answers, and they'd have some judge model that could pair up the ground truth answer with what the LLM outputted and give some kind of score associated with that. When it became kind of much more heavily used in the LLM world, we use things that involved human feedback, and we would train models that would then take human ranked feedback and project what other humans might rank about the output of a model, and then use that to train the base model. So you can imagine this all became very, very tricky and very fraught with layers of abstractions and layers of different kind of training loops all impacting each other. So there was a big change, a big revolution, which was moving to a model called GRPO. And the key insight here, and hopefully it's kind of clear from the diagram, and I can get into some of the details here, is just that we now have this thing called group computation. And so the group computation, largely the only change you should be considering here is that we're now using the model itself to train itself. And the way this is done still involves some kind of proxy evaluation, often related to, say, correctness or some other kind of ground truthable way of evaluating the model. And so that means that PPO is still sometimes used. You get SFT, PPO, and then GRPO oftentimes when training models. But the key idea here is that you're using the model itself to train itself. So now you're inferring the same weights that you're using for training. There's other things to note here, which is that if you note the KL, it's no longer used kind of as a single bias term. I didn't include the full equations, they get really complicated, but it's not used as just like this bias term in PPO to try to regularize it. It's actually used like very heavily to make sure that the model doesn't diverge too far from itself in GRPO. And there's a lot of stuff like this. And GRPO is not really the only thing used. There's a bunch of other variants that use group relative computations, but they often have these weird constraints, not weird, but justified constraints to try to make the model not kind of go off the rails when it's training itself. And you can imagine how unstable something like that could be, but how intuitive it makes sense, right? Like, it's like the best thing we have are these LLMs. Of course, they're probably the best things to judge themselves. So the way it works concretely is you have a bunch of responses. If there is a majority, that means it's not like all one way or all the wrong way when it comes to the judgment. If there's some majority, say it's like 7-3 right versus wrong responses, you now have some advantage. And this advantage can be used to calculate a loss, which can then improve the model. So a lot of the rollouts that you do are actually just to have no advantage and you can't even use them. And you can imagine that generating multiple responses only gives you a single training pass. So the inference workloads are now huge because you're doing a bunch of responses in parallel. These are full rollouts. These are not individual tokens. And then you're evaluating them at the very end. So inference is now incredibly important. We've got very, very sparse reward, and it's using the same model that it's training to do the inference. So this is all becoming extremely layered and extremely precarious. And it's starting to justify potentially why you'd want to be very careful about everything. And then IS weights came into the picture. So importance sampling weights are kind of an old thing. This is from a blog post. It's actually quotes the original paper. Sorry, I didn't include the original paper here that first talked about the specific formulation of importance sampling. But importance sampling largely allows us to do a bunch of rollouts, do a ton of inference, and then go back and update the original weights. The issue is that you can have like stale weights. So if you're doing inference with old weights and then constantly updating new weights, you're now inferring on like what is effectively a different model, and the loss doesn't really make sense, right? Like those gradients don't technically apply because you've just updated the weights. And in very large RL settings, this is necessary, right? You need some asynchronicity to like run things very efficiently. In huge RL settings, you can, I would claim you can do it on policy, and that's what we're going to talk about in a bit for very useful use cases. But potentially, if you have just like kind of a bootstrapped or cold start, you want to just do some like really, really huge scale async learning. So IS weights came into the picture, and all IS weights do, they're very similar to what the KL divergence term did in the earlier slide, is they just try to make sure the model doesn't go off the rails. And the way they do that is, I'm not going to derive it here, but you can just see They just take a ratio between the distributions and apply that as like a fix to what your update looks like. So if the distribution, when you're training it, say the logits that are outputted when you're doing inference compared to the logits outputted when you do the forward pass during the training run, if those are very different, if those diverge, that means you shouldn't update the gradients so aggressively and you scale them down. But if they're very similar, it means like, okay, this is kind of in domain, it's kind of the same model, go ahead and update gradients a lot more. And so this is like a huge correction term that's used everywhere. There's a bunch of variants. And this blog post, yes, thanks for the comment, is phenomenal. The whole blog is actually pretty good. So go ahead and check that out if you want more details. But this leads to kind of three things, or I guess four. One, very sparse rewards. And we're in the very last step of the training pipeline, which I didn't really comment on, but that means that we're in like extremely small loss scaling, right? So it's not like in a pre-training run where you have like the ability to, you know, use huge learning rates. You end up scaling everything down. So everything's like in this like kind of high frequency, like in the mantissa of the floating point. You're not like doing huge changes to parameters because you're the very last step of the training pipeline. And again, the rewards are really sparse. Two, this huge dependency on the execution of the main model itself, right? We're not in PPO space. We're not in some kind of like different judge that's helping to train it. We're just using the same, you know, model. So you can imagine that there's some compounding effects when you do that. And then three, there's just all these correction terms that have sprung up, right? Like GRPO has a bunch, IS weights are now very popular, and they mask out a lot of the numerical instabilities that may have been built from moving to lower and lower precisions. And effectively these days, everyone does RL and BF16. You'd want to do it in FP8 because it's a lot faster. And then finally, this blog post comes out. And this is kind of like the shocker that makes everyone reconsider kind of how we're looking at this stuff, which is that we're kind of ruining our models. And the reasoning there is just that, hey, there's a ton of stuff being shrouded by all the techniques we've piled on top of each other. And our bitwise exactness may not really be as close as we thought. And this blog post just proposes a different correction term. So this is now token-based importance sampling, which is useful and another thing to consider. But other people kind of were shocked by this. They're like, hey, let's look at other things. And so that's kind of the big thing, which is like, what if we just ditch all the correction terms and just use batch invariance, right? Have everything be bitwise exact and go from there. And that's what we tried to do. The way we did that is detailed in the blog post, and you can look at some of the code in TorchTitan. We basically aligned all of the kernels so that during the training run, you have the exact same batch invariance properties that you'd have in vLLM. So it's all basically just importing the vLLM work and then using that for the forward pass. TorchTitan then has backwards passes. So we had to like finagle those and make sure the backwards passes worked. But those don't need any kind of batch invariance because it's kind of undefined what a backwards batch invariance pass looks like. So we did that. And what we saw was actually pretty cool. The KL divergence. So this is the KL divergence term from the IS corrections. We'd actually use the correction term because I wanted to like show that if you don't have correction terms, it doesn't work as well. And then if you use bitwise invariance, it helps fix it. And you can see on the left, the KL divergence goes to 0. So it's like, okay, every single bit is exactly the same. If you run the same model with the same weights, there is a divergence and it's like pretty significant and measurable. And we're seeing that it's like, you know, spikes above 0.2, but that's noticeable, right? Like that's not 0. So this was really cool to see. But more interestingly, of course, are the two on the right. The first being entropy, which is just a smoother curve. Entropy is not really something that necessarily means that you've done a great job in terms of doing RL, but it's just, if it's smooth, it's probably a better bet and you do want it to go down. So it's like a good sign. But finally, the reward. Just turning on bitwise equivalence and turning on batch invariance magically makes the model train better. And this is sampled from one where I limited the output lengths to only be a certain size. So we capped the reward at like 0.7, totally artificial. If you were to uncap that length, it does go to like 0.99. It's a very simple task that it's learning. I forget exactly which one, some kind of math task. And you see this very drastically. And then if you run it longer, you'll see that the batch invariance off version crashes. Like it just irrecoverably breaks because it just doesn't have any of the stability that you get kind of for free when you do things very, very carefully. And so I think that this is kind of the the biggest results that was shown also in the blog post that I think is linked in the references from Wentao section, Horace's blog. And I see there's some questions that I'd be happy to answer. So what's happened if it's uncapped the reward limit? I guess, could you clarify what you mean by which part being uncapped? So there's an uncapped like length that will get closer to 1, and 1 is the maximum reward. It's just that everything's 100%. And then there's another question that came up. So there is one more slide. Let me just get through that, and then I'll go through and start answering the questions. And this is just kind of next steps as well as other stability tricks. So I don't want to just say like, oh, bitwise invariant or bitwise exactness and batch invariance is the only fix to all of this. There are other types of correction terms that have shown to be very useful. If you switch from BF16 to FP16, because like I mentioned, everything's kind of in the mantissa at this point because it's so late in the training regime, FP16 helps a lot. And people have shown that like, hey, these huge workloads like FP16 just magically solves it. So, you know, there's something there, but who's going to stay in FP16, right? Like we're moving to FP8, we're moving to FP4. So who knows if that'll hold true. I think bitwise exactness is still very important here. And then finally, you can use rejection sampling. I know a lot of folks here are familiar with speculative decoding. And if you use kind of the draft model to just be this non-bitwise exact and then use the training model as bitwise exact, you get kind of like an acceptance rate, which then you can infer how far away from, you know, the ground truth bitwise exact place you are. So it's kind of like using the KL divergence term more directly. It's not efficient. You use a ton of VRAM, but you could, in theory, do this. And what you get is basically very similar verifiable results. But if you just have a bitwise exact kernel, the acceptance rate is infinite. So then you just don't even need it at all. So it's kind of easier to just do this with batch invariance. So these are the ways to do it, just to be aware of. And then finally, next steps, I think just always improving the performance is always good in the hardware support. I know Wentao mentioned this. Compilation support, it exists in PyTorch. I think there's more to do there. It's interesting because split K is like an artifact of this old technique called R factor, which comes from halide. And compilation heavily leveraged the fact that you can just do R factors or split Ks to make things run faster. And now we're effectively peeling that back and saying, no, don't do any of the optimizations you learned how to do and do it much more dumbly. But I think we can go back and make it smarter based on workloads, based on like, if you're using speculative decoding, now you're in compute bound domain, you don't need to use split Ks as much because you can parallelize along batch dimensions, that kind of thing. And then finally, figuring out unification. This is mentioned in the blog post. SGLang has done a decent job of like showing how to get RL working with SGLang, and they have like trainers, I believe. It's a good story to say like, hey, we're using the same code for a lot of the forward passes, especially because inference is now like very dominant in the RL space and very important to get like state-of-the-art models. So figuring this stuff out is obviously going to be quite important. Cool. So I did not put an end slide, sorry, but let's maybe take some questions. I might need some help, Michael, on how you normally field questions. It seems like a bunch of
Yeah, there's some in-depth ones. Yeah, I mean, I think you're doing it all right. Yeah, maybe JMs. Are you doing any sequence mining? Like say.
Okay, so the question is, are you doing any sequence masking? There's some research that you can get around numerical issues, crashing the training by just masking out entire sequences when their importance ratios that are too large, greater than 10. Yeah, so that, I mean, that's very similar to kind of just any other type of correction term. It's just more of an active one where you're like doing something to the masks of the losses. So yeah, I haven't tried that personally, but it falls in line with a lot of these other techniques that are helpful for making sure things don't crash. Can you elaborate on how the KL div is 0 for the batch invariant case the model training skills? No, so that's the big thing. Like what we did was we actually unified the forward kernels with TorchTitan. So we genuinely got the KL divergence to be 0 by just calling the exact same forward passes. So TorchTitan was effectively using vLLM. It wasn't actually, there's a lot of hacking, but it was effectively using vLLM as its own forward operations. And then it had custom backwards that would apply.
I saw Ray raising his hand for a long time. So what's your question?
So I might have missed something, but first we were talking about like batch invariance. I believe it's basically getting consistent floating point errors. But then you introduce a new term called exactness, which seems to me to suggest that you don't have floating point errors anymore. So I'm just wondering, like, how did you get this new exactness?
Yeah, so I would say that batch invariance is a run-to-run invariance. That means that you can do, say, a prefill of a generated output and get bitwise exact equivalence between those two. So then that's where the exactness terms come from, which is that it's completely invariant to the inference, which is the forward pass. And now in this case, it would be the training pass, which is effectively just a prefill of what was generated. And we see that they're bitwise exact.
I see. So a lot of the benefits are from just matching previous inferences, so that like terms like Hale divergence, I guess, don't have extra errors from the influences from like the batch size or batch.
Yeah, so I guess one thing that was implicit that I didn't really concretely go over is that batching is effectively the same due to the fact that split K is well handled in the attention along the L axis. Batching is effectively the same as going from decoding to prefilling. So if you think of prefill as just being nothing more than batch decode just in the context window space rather than the batch dimension, and then you solve for that, you end up kind of with the utility that's needed for RL training.
I think.
Yeah, well stated. Really accurate words there. Do you happen to know if this helps in the async off policy case?
It's a good question.
Specifically, I guess.
Yeah, I guess how async. So no, to directly answer it, no, I don't. Yeah, I'd be hard pressed to say it would, like just intuitively guessing, because async, like the intrinsic staleness from running async causes issues that I would guess surmount in terms of magnitude the types of errors that you're accumulating when doing, pure on policy, non-bitwise versus bitwise exact. So my guess would be no. That being said, I have not personally tested this. If anyone else here has, I think that'd be really interesting insights.
Yeah, the only thing I've heard with respect, I mean, for async off policy, like getting the important sampling or whatever sampling you're doing right is like really important to kind of keep things on the rails kind of as you said it. Well, I mean, yeah, great presentation, everyone. Are there any other questions people have before we head off? Nope. Okay. Well, thanks everyone for coming in on this first one of the year. Like Sasha said, we have a lot more planned every week this month. Yeah, give a big thanks to Wentao and Bram for a great guest presentation. Yeah, and hopefully we can see a lot more collaboration and work in this space. Thanks everyone. Have a good